Okay, the recording is started. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraj. He is professor in IIT Delhi. This is the fourth week of 12-week course. And from the last 3 weeks, we have discussed like basic definitions of probability, basics of probability, conditional probabilities, Bayes theorems. And in second week, we will discuss about random variables. And in the last week, we have discussed about like moments and moments inequalities like Chebyshev's, Markov's, Jensen's, etc. Now, this is the fourth week. In this week, we will discuss about standard distributions. Okay, so there are some common distributions that are usually used, and those are discrete in nature as well as continuous in nature. So we will discuss those standard, discrete, and continuous distribution in week 4. Also, some applications of these random variables via these distributions. Okay, so the topic of today's slide. Standard distributions, in which we will discuss about discrete distributions, continuous distribution, and then we will solve problems on the basis of these distributions via defining random variables and applications of Okay, so up to week 3, anyone have any issue, then you can ask, or you can ask me later as well if you want. Okay. So let's start with some recaps of those 4th week lectures. Like we will discuss about discrete distributions first. Okay. Discrete distributions. Okay. So the first one is like constant distribution. Constant distribution, constant random variable. Okay. So those random variable that is like concentrated on a particular point, okay, on a particular constant only, then that is called constant random variable. The distribution is like defined as this, like probability that x is a random variable, which is said to be constant random variable if the probability that x equal to a equals 0, then this is called constant random variable. Okay, and this means only like we can also like this, like the probability comes out to be 1 when x lie on this particular point a, or 0 when x is not lie on that point. Okay, the second one is like Bernoulli distribution. Okay, so Bernoulli distribution like comes from like Bernoullian trials. Okay, Bernoullian trials are those trials in which we have 2 outcomes only. Okay, so sorry, so we have like an outcome which is termed as probability of success, and the other one is maybe you can call them probability of failure. So suppose x is a random variable. Okay, Just wait for. Sorry for the disturbance. Okay, so suppose X is a random variable. Okay, then we define the probability like P and 1 minus P and 0, where P is like we termed as probability of success. Okay, so when the probability is P, when it lies like X equals 1. Okay, and if X equals 0, we have only two outcomes, either 0 or 1, either true or false, either yes or no. Okay, so binary in nature, we have only two outcomes, either 0 or 1, with probability 1 minus P for 0 and P for 1, and otherwise. Okay, also like P, also the value of P lies within 0 to 1. Some people use 1 minus P as Q for this, for easiness. Okay, so this is the Bernoulli distribution. Okay, and in this case, the expected value that we have already discussed in the previous class, the moments, the first order moment. Okay, the expectation is like P, and the variance is like P and 1 minus P. Okay, we can discuss it in general form as well. Okay, so this is the Bernoulli distribution. When we have only two outcomes, then the probability mass function is defined in this manner. Okay, the third one is like binomial distribution. Now the binomial distribution, in binomial distribution, suppose we have a random variable X, this follows binomial distribution. Okay, with the parameter N and P. We have two parameters, N and P. Okay, so this is called binomial distribution with the PDF N C x P to the power X 1 minus P to the power N minus X. Here X, the support ranges from 0, 1, 2 up to N. In a similar manner, P lies between 0 to 1. Okay, so this is the binomial distribution. Here in binomial distribution, N, the number of trials is fixed. Okay, and the number of trials is fixed, and X is a random variable actually. In the letter, we will discuss why I'm writing this particular point. Okay, X is random variable and the number of trial N is fixed here. Okay, and the expectation, the expected value in this case is like, since it is a discrete random variable, so we will use X summation X into probability that X equal to X. X ranges from like 0 to N. Okay, and after putting these values and solving, we will get N into P. Okay, and variance of X, which is equal to expectation of X square minus expectation of X whole square, and after solution, we will get NPQ. Since P, okay, not Q, let me write it 1 minus P. We can write Q for the simplicity purpose. Okay. So, so NPQ is there. Okay. Here you can see that like variance of x is less than expectation of x in binomial case. Also, we have some remarks. Okay. The first remark is like suppose when we take n equal to 1. Here, if we have considered n equal to 1, then on the basis of n, the value of x is either 0 or 1. So this converted into Bernoulli distribution. Okay. So in that case, the binomial distribution converges to Bernoulli distribution with same probability of success p with n equal to 1. Okay. Also, we have other remarks as well. In a similar manner, like okay, we will also discuss. Suppose x1 follows like Bernoulli distribution. We can write Bernoulli distribution either this form or binomial 1 at n equal to 1, then it turns to Bernoulli. Similarly, x2 follows 1p and so on, xn follows Bernoulli distribution. Then the random variable, which is summation over xi, I from 1 to n. Okay, this we have considered x. This may follow binomial distribution with parameter, since we have considered n random variables, so n, and the probability x success is p. Here the probability of success is like common in all the case, and these x1, x2, xn are actually independent in nature. Okay, then this property holds. Now the next, like we can use mxt, moment generating function. So moment generating function is like q plus p e to the power t whole to the power n. Okay, q is here 1 by p, sorry, 1 minus p here. Okay, so you know that, na? Like expected value of e to the power tx, the expectation of e to the power tx is moment generating function, and after putting the after solution, we will get this. And if we put n equal to 1, then mxt for Bernoulli comes out to be like q plus p e to the power t. This is for Bernoulli. Okay, Bernoulli distribution. And yes, we have discussed about mean variance, mxt, or you can also calculate the mean and variance, either this formula, okay, either this formula, like expected value of x, or you can use the differentiation of mxt. You can differentiate the mxt and then putting the value of dummy variable t equal to 0, and then you can find the non-central moments, and with the help of those non-central moments we can calculate the mean and variance of the distribution. Even other higher central moments can also be estimated. Okay, also there is one more remark. Since here these are the parameters, okay, here the n and p are the parameters for the binomial distribution. Okay, so the values of n and p like characterize the distribution given. So like if p equals half, p is like greater than half, and p is less than half. There are three possibilities. Okay, for a like sufficient large n, if we have three values of P, because P lies between 0 to 1. So we have three possibilities. So when P equal to half, then the nature of the curve or the nature of the distribution is like symmetric. Okay. And for greater than half, it is like negatively skewed. Do you people know like symmetricity and skewness of a distribution? Anyone? If you don't know, then I can explain in a pictorial form positively.
Please explain it, sir.
Sorry, like you are not audible. Okay, let me explain in a simpler manner. Okay, like on the basis of shape, okay, we can define. Okay, just suppose we have three PDF. These are the probability density function. I can like draw for continuous distribution even. Just I want to give the concept. Suppose if we have a point here like this, which have a line of symmetricity. Okay, so this type of distribution is called like symmetric. This type of curve is called symmetric. When the most of the probability is distributed in the first half. Here, like in the first half, most of the probabilities are distributed. So it is called positively skewed. These are skewed. The both the latter one are skewed, but it is called positively skewed because the most of the data lie within the first half. Okay, the most of the probability is distributed within the first half. So it is a positively skewed. And like in a similar manner, the most of the data distributed in the second part or the latter part. So it is called negatively distributed, negatively skewed. So in general, normally we can see the binomial distribution is positively skewed, but for some values of P, maybe it negatively skewed as well. And if for large, sufficient large n and P equal to half, then it is symmetrical in nature. Then the first one, this curve will be like we get. Okay, so these are the properties of the binomial distribution. We can discuss about like skewness, kurtosis, and dispersion, the different descriptive statistics in the ninth week of this lecture, actually. Okay, so in the ninth week, we will discuss it in detailed form, how to measure and all. The next distribution is like geometric. Look, every distribution is used in some conditions. Like for a binomial distribution, we have some assumptions. Okay, like we have some assumptions here. The P, the probability of success must be constant in each and every trial. Okay, and N should be finite. Then only we use this distribution. And the value of N is not like much. Sorry, the value of P. The value of P is not like near about 1 or near about 0. It may be in between, but if smaller the value of P, then it converges to some other distribution that we will discuss later. Okay, now geometric distribution. Like this distribution is used when we have like dealing with those type of question in which first success is required. Okay, when we get the first success, then those kind of problem, those nature of problem comes under geometric distribution. The PDF or the sorry PMF, actually PDF and PMF are similar things, but PMF we use PMF when we are dealing with a discrete random variable. Okay, so probability mass function under geometric distribution will be like 1 minus P to the power 1 minus X. Sorry, it's X minus 1. X minus 1 into P. Here P is the probability of success and 1 minus P, which is also written as Q, is probability of failure or probability of not getting a success. Okay, X equals 1, 2, 3, and so on. Like example of geometric distribution, suppose we tossing a coin, okay, and getting the first head will win the match, for example. Then it may possible you may try, you may make like you may take 7 trial to get the first head. You may take 9 trial, or you may take the first trial as well. Okay. So when we get the first event, when the first time the event has happened, then that kind of problem will be solved with the help of geometric distribution. Okay. It has like similar, the value of p should also be lie within 0 to 1, excluding both. The expected value, the mean, is 1 by p, and the variance or the variability of the geometric random variable is 1 minus p upon p square. Okay. And similarly, sir has already discussed these things. I'm just writing as a formula. So p e to the power t upon 1 minus p e to the power t. This is the mxt of geometric distribution. This is now we can use the help of this moment generating function to calculate the other higher moments as well. Okay. Now the next one is negative binomial distribution. Okay. Negative binomial or inverse binomial, some people say. Okay. It is also used, or also it is like Pascal distribution. It is also like termed as Pascal distribution. This distribution is used when we define, suppose we want R number of success, a finite but more than one number of success in a trial, in a number of trials, then that kind of problem can be solved with the help of negative binomial distribution. Okay. Like the PDF of this, let me first write. The PDF or PMF, sorry, I'm usually habitual of using the word PDF. Okay, so the PMF, the probability mass function, is defined as like this: x minus 1 c r minus 1 p to the power r, and 1 minus p to the power x minus r. Similarly, here x start, the value of x start with r plus 1, and so on. Okay, and p lies within 0 to 1, the probability of success. Okay, actually, negative binomial distribution is a generalization of like geometric. Suppose we put the r, r is termed as number of success. Here, r is like number of success. If we have considered r equal to 1, then this negative binomial distribution converted into geometric distribution. Okay. So, and here also, like here x and r. Here r is a like fixed, but x is a random variable. Okay, so the random variable here, x is the number of trials we have performed. Suppose we toss a coin 7 times, or we toss a coin up to when up to until we get 3 head. Okay, 3 successive head. Suppose I am telling we toss a coin up to that number of time until we get 3 heads successively. So in that case, getting 3 hits successively means we have fixed a number of success. But the number of random variables, the number of trials is undefined here because it may vary, maybe infinite. So that's why the value of x may take value from r plus 1 up to infinity. So in binomial distribution, the n is fixed, but the number of success is random variable. Here it converts, it inverse actually. So that's why some people termed as negative binomial distribution as inverse binomial as well. Okay, sorry. So this is, and the number of success is fixed. Okay, we will discuss about these things actually with numerical so that we have better concept. Like the expected value here is like x by p. The variance of the negative binomial distribution is like R1 minus P on P square. Okay. And the MXT will be E to the power T 1 minus P e to the power T whole to the power R. If you see these things, okay, and for the geometric distribution as well, the only difference is multiplication of R, and in MXT, the power R. Okay, so we put the value of R equal to 1, then we get the mean, variance, and moment generating function for the geometric distribution. Okay. Now the next one is Poisson distribution. This distribution is like quite used in everyday life even. Okay, when we are discussing about the rate, okay, or we have a very less probability of success. So in that kind of scenario, we use Poisson distribution. The probability mass function for this distribution is like e to the power lambda, lambda to the power x upon x factorial. Here x may take value from 0, 1, 2 up to, and the value of lambda is greater than 0. Okay. And we can also denote this, suppose x is a random variable that follows p lambda, that is the Poisson distribution with parameter lambda. In Poisson distribution, there is only one parameter. Okay. Now the mean, the expected value of x will be the lambda itself. Okay. And the variance of the x is also the lambda only. And the moment generating function for the Poisson distribution, e to the power lambda e to the power t minus 1. Okay. So this is the moment generating function and the first and second moments for the Poisson distribution. Also, like we have Bernoulli distribution. Suppose x, suppose, okay. Suppose x follows binomial distribution with parameter n and p. If the value of n is quite large, okay, tends to infinity, that means quite large, and the value of p is quite small. So in that scenario, this x converges into Poisson distribution. Okay, this binomial, okay, let me write binomial here. This binomial distribution it converges to Poisson distribution. Okay, if n is quite large or p is quite small, in this scenario, this distribution converges into this with lambda equal to n into p, with the parameter lambda equal to n into p. Okay. Okay, now there is one more distribution, discrete uniform distribution. Discrete uniform distribution is actually used in daily life as well. Like when I'm telling you, just guess a random number between 0 to 100. Okay, integral number, or guess a random number between 0 to 1 or 5 to 7, or okay. So these are the random numbers. Okay. Discrete means it can take value up to integral value, then it is a random, discrete and uniform. Otherwise, it is a continuous uniform distribution. The PDF is like 1 by n, where x lies x1, x2 up to xn. And what is n? Here xi belongs to like any real number. Like throwing, like rolling a die, getting 1, getting 2, getting 3, getting 4, getting 5, and getting 6 all have the same probability of 1 by 6. Okay. So these are the discrete, the example of discrete uniform distribution. Here, if you can see, its expected value is nothing but the average. Okay, like 1 by n, since the PDF or the PMF is independent of the random variable x itself. So 1 by n summation of xi, sum divided by the total number of observations that we usually termed as like average. Okay. And in a similar manner, you can calculate the mean variance and MXT as well. Okay. Now, up to this point, we have discussed some common discrete random discrete distribution. Now, from here onward, let's start with continuous distribution. Okay. So in continuous distribution, the first one is continuous uniform. Let's start with continuous uniform. Okay, like here in discrete uniform distribution, we have the support x has integral value, and in continuous, it contains in range of values. So since we are discussing about continuous random variable, so we use a PDF and it is denoted as fx 1 upon b minus a when like x lies between a to b and 0 otherwise. So this is the PDF of the continuous uniform distribution. Okay. The even you can also write the CDF of this distribution by integrating it. Okay. By integrating minus infinity to x fx dx, and after calculating x minus a upon b minus a is the cumulative distribution function for the continuous random variable. The expectation in that case is a plus b upon 2, and variance is 1 by 12 b minus a whole square. Okay. Now mxt is also there. The moment generating function e to the power bt minus e to the power at upon t of b minus a. This is the mxt. Also, if you can like a characteristics function can also be psi xt can also be calculated by putting I with t only. Okay, so e to the power I bt minus e to the power I at upon I times of t and b minus a. Okay, so that's why we have not mentioned characteristics function till now, because we can use the mxt with I, then it convert to characteristics function. Okay. Now the next one is exponential distribution. It is also one of the most useful distribution. Actually, any kind of like equipments, electronic equipments have lifetime. Okay, and those lifetimes may follow exponential distribution. Okay, any kind of electric bulb, electric motor, or any kind of devices will follow exponential distribution with ranges of values of parameters of sorts. Okay, so this can be denoted as like this. Suppose x is a random variable, it is a continuous type random variable which follows exponential distribution with parameter, suppose lambda. Okay, so the PDF of the exponential distribution is lambda e to the power minus lambda x for x is greater than 0. That means 0 to infinity, and lambda should also be greater than 0 and 0 otherwise. Some people use the CDF. Okay. Some people use the PDF as this even. They replace lambda with 1 by lambda actually. Okay. So you need to be careful while using this. So because the mean and variance may change on the form x is greater than 0, lambda is greater than 0, otherwise. Okay, so I'm taking this. Okay. I'm considering this that I've written in like red color. Oh, okay. So in that case, the CDF 1 minus e to the power minus lambda x for the same support. This is the CDF. The expected value of x is, if we have considered lambda e to the power minus lambda x, then the mean is 1 by lambda and the variance of the random variable is 1 by lambda square. Okay, but in case, suppose some people may use the blue one, the form of written in the blue color, then in that case, it must be lambda and variance of x is lambda square. So please be careful while using the form. Okay. Now from onward, I am using the red color, the form that is written in red color. The next is like mxt, the moment generating function. The moment generating function is 1 upon 1 minus t by lambda. Okay, this is the moment generating function for the exponential distribution, and it by lambda is the characteristics function. This exponential distribution has a specific property which is termed as memoryless property. Memoryless property, or some people call it Markov property, or some people call it lack of memory. Lack of memory property. Okay, so what is this property? This property, like the probability that x, the random variable x, may take value t plus s, given the x is greater than s. That means the product, suppose x is a lifetime of a product, and the product x is survive up to point s. Then what is the probability that the product x is survive up to point t plus x? Is nothing but the probability that it survive greater than t. Okay, so this is the property, because what happened in previously, it forgets, maybe you can say. So it lacks the memory of what has already happened. So that's why it is called memoryless property. You can also see, uh, since like probability of x is greater than t is nothing but 1 minus probability of x is less than or equal to t. Okay, so the CDF is, and this is nothing but the CDF actually. If you see, this is the definition of CDF only. Okay, this definition of CDF, 1 minus e to the power t. So this comes out to be like the probability x is greater than t plus s, given x is greater than s, is probability that x is greater than t, which is equal to e to the power minus lambda t. Okay, so this is the memoryless property. Now the next is also, yes, even let me write one more remark, not from this distribution. Actually, geometric distribution also holds the same property. Geometric distribution also holds the lack of memory property. Yeah. So lack of memory property is only like validate under two distributions. The one is geometric distribution, which is discrete in nature, and the second one is exponential distribution, which is continuous in nature. So this may also a question. Okay. Now the next question is, okay, let me write on the next page. Gamma distribution. Okay, these are the lifetime distributions. Okay, we use this kind of distribution in our most of the works. These distributions are used. Okay, suppose X is a random variable which follows gamma distribution. It has some parameters. Okay, suppose lambda and R are the parameters. So the PDF of the gamma distribution is like lambda to the power R upon gamma R. Gamma R is a gamma function. We will define it later. X to the power R minus 1 and e to the power minus lambda x. Here lambda is greater. Lambda is strictly greater than 0. X is also greater than 0 from 0 to infinity. And for R as well. All the quantity are like greater than 0, strictly greater than 0. Lambda, X and R all. Okay. Here gamma R, if you people know, gamma R is a gamma function which is defined as like 0 to infinity e to the power R minus 1 e to the power minus t dt. Okay. And if also if like R is positive integers, then in that case, suppose R equal to n, we have considered for numbers, we use n as, okay, we prefer n to be used. So gamma n is nothing but n minus 1 factorial when n is or R is an integer. Okay. So we have remarks for the gamma distribution as well. The first one is like, suppose at R equal to 1. We have two parameters for the gamma distribution, lambda and R. When we consider R equal to 1, then this gamma distribution converges into, can anyone tell me? This gamma distribution converted into which type of distribution when we have considered R equal to 1? Sorry?
Exponential distribution.
Exponential, exactly. You may check even by putting the value of R equal to 1 in the PDF of the gamma distribution. Okay, so these are actually the properties that we will use in in future. Suppose we are dealing with the statistics problem or any probability problem, then we use these properties to solve the question. At R equal to 1, uh, this gamma R lambda actually converges into exponential lambda at R equal to 1. Okay, so it is one of the property. Okay, now also we have second when R is a positive integer. Okay, we have already discussed, but name them. When R is a positive integer, when R is a positive integer, then in that case, this distribution is called Erlang distribution with the same R and lambda. We are not like differentiating these things. Since the positive integer, in that case, we put R equal to n if we want. If not, then R lambda can also be used. Okay. So in that case, this is Erlang distribution. But in general, we use gamma, R lambda, and not mentioning these things. But we should know what is the meaning. Okay. So the third one is also there. Like suppose uh, x1 follows exponential with lambda, the similar. X2 follows exponential lambda, and in a similar manner, xn follows exponential lambda distribution. Lambda distribution also x1, x2, xn are independent random variable. independent random variables, then in that case, the x, which is defined as the summation of xi, okay, this follows gamma distribution with n lambda parameter, or since these are the exponential distribution, these are the numbers x1, x2, then Erlang distribution, whichever you want to write with nn or r or lambda. Okay. Now the mean and variance of this distribution will be expectation of gamma variable is r upon lambda, and variance is r upon lambda square. If you like remember, the when we put the r equal to 1, the gamma distribution converges to Poisson distribution, sorry, exponential distribution. Here, when we put r equal to 1, the expectation of exponential distribution is 1 minus lambda, which we get from here. Okay. Also, the moment generating function for this is lambda upon lambda minus t whole to the power r. Okay. So less than lambda, this should also be the condition. So this is the gamma distribution. Now the next distribution is beta distribution. For beta distribution, suppose x follows beta, we have two parameters, alpha and beta, suppose we have considered. Okay. So the form of the PDF is beta to the power x to the power alpha minus 1, 1 minus x to the power beta minus 1, and the beta function of alpha beta. Okay. This b alpha beta is the beta function of alpha beta. Here, like alpha is greater than 0, beta is greater than 0, and x lies between 0 to 1. Okay. So this is called the beta distribution. Where like beta function is defined as 0 to 1 t to the power alpha minus 1 t to the power beta minus 1 dt. Okay, so from this we can see that it is a proper distribution because the integral of this PDF comes out to be 1, or or in general we use the beta function with the help of the gamma function as well. Gamma alpha, gamma beta, gamma of alpha plus beta. Beta function of alpha beta is nothing but gamma alpha, gamma beta upon gamma alpha plus beta. Gamma function has already defined in the above. Okay. Now the average or the expectation or the mean. The mean is like alpha upon alpha plus beta, and the variance of the distribution is alpha beta upon alpha plus beta plus 1 times alpha plus beta whole square. This is the mean and variance of the beta distribution. We can also use like MGF, and with the help of those, further moments can be calculated. We can done these the first four moments when we are discussing about the skewness and kurtosis of the distribution. Okay, there is one more distribution. There is a lot of distribution actually, like Cauchy distribution, Cauchy, whatever you like. Okay, so fx, the PDF format 1 upon gamma beta, okay, and 1 upon 1 plus x minus alpha upon beta. Okay, so it has two parameters, alpha and beta. Okay, so Cauchy alpha and beta. The notation for this distribution, again, its range from minus infinity to infinity. If if we have considered alpha equal to 0 and beta equal to 1, then in that case, this generalized Cauchy distribution is converted into a standard Cauchy distribution, which is like P01, and the form of the standard Cauchy distribution is like the value of 0 and that to 1 upon 1 plus x square x 0 to. Okay. If you calculate the mean, then you will find that the mean of the Cauchy distribution does not take place. There is a remark for the Cauchy distribution. Mean distribution does not. Okay. So besides mean, we use median and other statistical characteristics or central tendency for the further discussion when we discuss about the distributions. Okay. Now the most important distribution. Let's change color. And it is normal distribution. People call it Gaussian distribution. Okay. So the normal distribution, suppose x is a continuous random variable. Okay. So it follows normal distribution with parameter mu and sigma square. Okay. The notation is sigma square. This is wrong. Okay. This is wrong. To make sure, when this type of notation is given and mu sigma square or n numbers are there instead of mu and sigma square, then always remember, okay, it is sigma square, not sigma. Okay. And the form of the PDF for the normal distribution, 1 upon sigma root 2 pi e to the power minus 1 by 2 x minus mu upon sigma whole square. Here the support ranges from minus infinity to infinity. The mu is the location parameter, which is also ranges from minus infinity to infinity. And the sigma is a scale parameter, which is greater than 0. Okay. So this is the form of the normal distribution or the PDF of the normal distribution. Okay. When you write the CDF of this distribution, you will find that it is not possible to integrate this PDF. So like some numerical methods are used there to find the CDF, but not in closed form. So we have some tables for the normal distribution. And that's why we use the transformed version of the normal distribution most of the time. Okay. So suppose Z is another random variable which is defined as x minus mu upon sigma. Okay. So in that case, this Z will follow the normal distribution as well, but with mean 0 and variance 1. Mu is the location parameter. We shift, we take differences. Okay, x minus mu. So mu minus mu comes out to be 0 and divided by sigma comes out to. So mean and variance of the standard normal distribution is 0 and 1. Okay. And for the normal even as well, right? Expectation of x. X is a normal random variable and Z is a standard normal with 0, 1. The expectation of x is mu as well and variance of x is sigma square. That's why we use n, mu and sigma square. Okay. And if I am writing expectation of Z, it comes out to be 0 and variance of Z is 1. Okay. Also, the PDF should also be written here. The PDF of standard normal distribution is 1 upon root 2 pi. Okay, from here sigma equals to 1 and e to the power 1 by 2 x minus 0 upon 1, that implies z is, okay, and the value of z lies between minus infinity to infinity. Okay, so we usually use this form, okay, when we are dealing about the some numerical probability of normal distribution. Expectation variance. Now MXT is also there. The moment generating function for the x, I have used x, that means for the normal distribution with mean mu and variance sigma square, the MXT is exponential of mu t plus half of t squared sigma square, half of t square. So this is the mean variance and the moment generating function for the distribution. You can put the value of mu and sigma square at 0 to find the MXT of, oh, sorry, the moment generating function for the standard normal variable. There is one more remark for the normal distribution. There are lots of remarks actually. Those remarks are questions. One thing is like the distribution. Suppose since it is mean minus 3 sigma, x is normally distribution. X is normally distributed with parameter mean mu and sigma square. Then mu plus 3 sigma. Then in that case, the within 3 sigma limit, the possible allocation or the possible probability distribution lies within 3 sigma limit, and this is nothing but 99.73% or 0.9973% of the data, uh, like included within the 3 sigma limit if the random variable follows the normal distribution. Okay, so we have like much information regarding this. Also, there are some more distributions are there, like log normal distributions are there. Okay, suppose x is any random variable, okay, which follows log normal distribution with parameter mu and sigma. Mu sigma constant. If x is a log normal random variable, if log of x is normally distributed. Okay, the PDF. Let me write the PDF for this distribution. 1 upon sigma x root 2 pi e to the power half x. We replace x with log x actually. Yes. Minus half is there, and log of x minus mu upon sigma whole square. So this is the PDF for the log normal distribution. Here the support, here the plus point is support is greater than 0. Since we are dealing with the different kind of like lifespan of any kind of equipment or survival time of person from any kind of disease, then that must be positive. No? So that's why uh, log normal distribution is widely used in life testing methods. That will be used. Also, like the expected value of this is exponential of mu plus sigma square by 2, and the variability or the variance of the random variable, the log normal random variable is exp of sigma square minus 1 and exp of 2 mu plus sigma square. You don't need to like learn these things. Okay, the before the log normal, you should like remember the mean variance and MGF so that our calculation is faster. Okay. So in a similar manner, we have also different kind of distribution like Laplace distribution, logistic distribution. Weibull distribution is also one of the famous distribution we have used mostly. Pareto, and then chi-square T and F distributions are also there that are small sampling distribution that will be discussed, I think, in the statistical inference part, maybe. Okay. So these are the distributions commonly used, like discrete and continuous distributions. Okay. So if anyone have any doubt up to this point, uh, they can ask. If not, then we have some numericals on the basis of these distributions that we have. Is there any question? Okay, then let's start with some numerical. Sir has already discussed one question. Let me write the question as well. A fair die, a fair die is rolled 5 consecutive times. Okay. A fair die is rolled 5 consecutive times. Okay. Let x be a random variable. Let x be a random variable representing the number of times. Representing the number of times that the number 5 was obtained. The number 5 was obtained. Okay. We need to find the probability mass function, or in short, PM of the random variable. Okay. So our aim is to these are the given information. Which kind of distribution is this? Our aim is to find out which kind of distribution is this, the random variable x. The first one is either it is discrete or continuous, and with the nature of the question, you may definitely know it is a discrete in nature, because we are rolling a die, then either 1 or 2 occurs. No? There is no possibility of 1.2 occurs. So it is a discrete type distribution. Okay. And but there we have like 6 or 7 types of discrete type of distribution at up to this point. So let's start. Here we are given a die. Okay. So probability that a die. Okay. Any number have a probability 1 by 6 for I equal to 1, 2, 5, and 6. Okay. Now the random variable x, the definition of the random variable is the random variable x is a function from the sample values. The sample values taken from the sample space, okay, to a real number. Okay. So here the real number is like number 5. Our event is like 5. Okay. So we define the event getting 5. When we roll the die, getting a 5 is the event A. So what is the probability of getting the event A? The probability of getting the event A is 1 out of 6, and the probability of not getting the event A is 5 by. Okay, these are the information that are given in the question. Okay, so we have like roll this die 5 times. Okay, so we have two options: either getting 1 by 6, getting 5 with probability 1 by 6, or not getting 5 with probability 5 by 6. So it is a kind of Bernoullian trial. So that means we have two outcomes: either getting a 5 or not getting a 5, with probability either 1 by 6 or with getting probability either 1 by 6 or 5 by 6. Okay. And we repeat this Bernoullian trials independently. How many times? 5 times. Okay. 5 times. So in that case, uh, x1 follows Bernoulli distribution, x2 follows, and f5 follows. So summation of this, they follow binomial distribution with parameter n and p. So from here, it is clear that x, which is the random variable here, follow binomial distribution with n and p. Okay, x is a binomially distributed random variable with the parameter value of n equal to 5 and p equal to 1 by. Okay, so you can make questions itself even. We are given this question only. Okay, then if we roll a die 5 times, 5 consecutive times, let x be a random variable representing the number of times the number 5 was obtained. Then find the PMF. Okay, we have got the PMF because it is a binomial distribution with the given parameters. So the PMF of binomial distribution is NCX p to the power x 1 minus p to the power n minus x. Okay, x 0, 1 up to n, and p lies between 0 to 1. This is the standard PDF of binomial distribution. Now putting the value of n equal to 5 and p equal to 1 by 6, we get the distribution, the PMF for this particular example. So 5cx 1 by 6 to the power x and 1 minus 1 by 6, that comes out to be like 5 by 6 to the power 5 minus x. When x is ranges from 0, what is x? X is number of times getting 5 now, and we roll 5 times. And we roll the die 5 times. So either we get x equal to 0, means no 5 will occur up to in 5 rolls, or 1 or 2, or it may possible in all the 5 trials we get 5. Okay, so the value of x may take the value from 0, 1, 2, 3, 4, and 5 only. So this is the PMF of the Bernoulli distribution with the given value of parameters. Okay, now you can make your own question. What is the mean and variance of this particular distribution? Can anyone tell me? Look, the, when x follows Bernoulli distribution, the mean is NP. So this implies n equal to 5 into p equal to 1 by 6, out to be 5 by 6. And variance of the NPQ 5, q is nothing but 1 by p actually. Okay, 1 by 6 into 5 by 6 comes out to be 25 upon 30. Q equal to 1 minus. Okay, so you can construct many kind of question, a single question even. We have also one question here, like the number of patients who. Let me write some other question, then I'll come to this part only. The question is, suppose any device has a lifetime t, lifetime of any device t is followed exponential distribution with parameter 1 by. Okay, uh, find the reliability. Find the reliability of the product after t equal to 200. Means after 200 times, maybe it may be hours, minutes, months, whatever. So after 200 unit of time, what is the reliability of that product, which follows exponential distribution with parameter 1 by 100. Okay, so we are given like here t is given follows exponential 1 by 100. Okay, so 1 by 100 is there. So fx by t. So the distribution, the PDF of the exponential distribution is lambda e to the power minus lambda x, or lambda is greater than 0, x is greater than 0. Okay, and here the value of lambda is 100. So okay, so this comes out to be 1 by 100 e to the power minus p by lambda is already there actually. P is greater than 0. Okay, now we need to calculate the reliability that the product will last more than 200 unit time. So the reliability of the product P is P equal to 200 is defined as probability that P is greater than 200. Okay, the reliability is defined as probability that X is greater than the reliability is defined as probability that X is greater than. And you people know, na, the CDF is defined as how? See that X is less than or equal to X. So these are like complementary to each other, if you can see. So we can write is like 1 minus probability that T is less than or equal to 200. Okay, and since it is the exponential distribution, since T is exponential distribution, so in that case, the CDF of the exponential distribution is 1 minus e to the power minus lambda t, which is equal to t by 100. So putting the value in this and after solving, one minus e to the power minus t by 100 at t equal to obviously at t equal to 200 only. So after solving, we get e to the power minus t upon 100. Okay. So now we need to okay, I missed one thing actually, the probability here. So we use the probability as well. After solving like 0 to 200, since up to this point, it is t is less than or equal to 200. So probability that 0 to 200 is there. Okay. So either you may use direct this or direct this formula. And it is 1 by 100 e to the power minus t by 100 dt. And since e to the power t is like after integration, it again comes to b to the power t. So after solution, we will get e to the power minus 2, which can further be simplified as 0.534. This question is already discussed in the lecture actually. I'm just writing and showing you like how any kind of distribution is there and then how we can calculate the probability, reliability, or hazard rate function even, or any other statistical terms. Any statistical characteristics can be calculated once we know the parameters. we know about the distribution of the parameters, then every statistical characteristic can be calculated or estimated. Okay. Now we have one some questions actually. Okay. Like suppose X is a random variable, which is the height of adult male in a certain city. Let X be a random variable representing the height, of adult males in a certain city. Okay. And also we are given with mean height 175 centimeter and standard deviation of 8 centimeters. Now our aim is to like find probability that a randomly chooses person has height greater than 185 centimeters. Okay. Also, one more question is there. Find the probability that a randomly selected adult or male have a height lie within 170 to 185 centimeter. Okay, so these are the questions. Since we are already given it is a normally distributed random variable, so let's start with how to proceed. Can anyone tell me how to proceed this type of question? That has already discussed actually. Is there anyone want to say anything?
Chebyshev inequality.
Chebyshev's inequality. Okay. Look, we can use Chebyshev's inequality when what is the condition? Can you remember what is the condition for using the Chebyshev's inequality or any kind of inequality? Anyone? Look, Chebyshev's inequalities is used when we do not have the information regarding the distribution. But here we have the information that the random variable X is following normal distribution. Then don't need to use any kind of inequalities here. If we do not have the information regarding the distribution of the random variable and we have only the average or the mean and variance of the distribution, then we can use Chebyshev's inequality to find the lower or upper bound. Okay, but here we have the distribution that is normally distributed random variable only. So don't need to use any kind of inequalities or bounds here. Direct we can use the normal distribution. Okay, let me try this. X is a height of males. Okay, height of males in a particular city. And we are given it follows normal distribution with average or mean 175 and standard deviation is 8 actually. So we need to write 8 square here for the variance. Okay. So this is how the random variable X is distributed. Now, okay, let's start finding X is greater than 185. See, as I have told, na, because how can we solve this? From 185 to infinity. Okay, fx dx. This is how we solve this question only. Okay, but the problem is we are not able to integrate this integral, not closed form. This integral is not in closed form, so we can't solve this. So we use the standard normal property and standard norm. First, we standardize this x random variable. That means we transform the x random variable in z random variable, and then standard normal table is used to calculate the probability for this question. Okay. In any kind of normal questions, normally distributed question, okay, every question is solved with the help of standard normal table. If we are dealing with the probability, then we need to use the standard normal table. And for that, we need to standardize the random variable first. Okay, so this is not possible actually. This is not possible to solve this by via this method. So the probability that x is greater than 185, we can also write like this. X minus mu upon sigma is greater than 185 minus mu. Mu is nothing but 175 upon sigma is 8. We can write like this only. Okay. Then this is x minus mu upon sigma is z. Okay. Is greater than 185 minus it's this, or probability that z is greater than 1.25. Look, now we have solved most of the question actually. The rest is depend on which kind of or which type of table you are using to check the values. Okay. Okay, let me first draw the pictorial like pictures for this or the graph for this particular. So suppose it is a standard normal curve. Okay. Then this must be z equal to 0, z equal to 1, z equal to 2, z equal to 3 in a similar manner, -1, -2, -3, and so on. Okay. So this is the standard normal curve actually. And we need to find the probability that z is greater than or equal greater than 1.25. So the point is greater than 1.25 will lie near about this point. Okay. So this is the 1.25 and z is greater than this point actually. So this means we need to calculate the area of this standard region. Okay, now we need to use a normal table that I have like means pasted here actually, the second page. I'm just showing you like how we check this distribution. Here first, let me write it the first table, the second table. Okay. Now using the first table, if you can see, okay, there are we are given some values, na 0 point something and then 0.00. So suppose we need to check 1.25. Then in like column, we will go for 1.2, which is here only. Okay. And then with the help of this 1.2, then in that particular row, 0.05. So which is here. And the common point is this. Okay, so this is the probability for that for 1.25. Okay, but how? There is no curve actually given. So let me draw a curve even. Look, the caption of the table, standard normal distribution. Table values represent area to, sorry. The table values represent area to the left of the Z score. Okay, so that means if this is the Z score, then the table value gives the area of this side only. Okay, that means probability that Z is less than or equal to Z. Okay, this we are given this table in this format only. Okay, and we need to see. You can like either take a screenshot or whatever, which can like help this. See, Z is less than or equal to Z. We are given the table for the area to the left of the Z score. Now I'm going to the question. Okay, here we are given in the right format actually. Okay, in the right side of this particular. We know that the area under the curve is 1. Okay, so we can write this question 1 minus probability that Z less than or equal to 1.25. Okay, we can write this question in this format as well. Okay, and from the table, the value of this is given actually. The value of this is 0.89435. And after solving, we will get 0.10. It's 555 or 565. I think 565 is there, na? Okay. Okay, so this is the probability for a randomly chooses male having height more than 185 centimeters. So around 10.5% chances are there that a random chosen male has a height more than 185 centimeter. Okay. Is it clear like how to read the table and how to draw the curve? Because every time when we are dealing with the normal distribution related problem, then this curve should be drawn. Okay, so that we have a better insight how to solve the question. Okay, we have also like one property of the normal distribution. I'm discussing that, but let me first write the second question. The second question is what is the probability that the average height of the male lie within 170 to 185 centimeter? Okay, in a similar manner, the probability 170 minus 175 divided by 8, it's x minus mu by sigma. It's 185 minus 175 divided by 8. Okay, and then if you solve, you will find minus 5 by 8. It's z. It's 1 actually 10 by 8 is there, and we can write like this minus 0.625 z 1.25. Okay, again we need to draw the curve so that we have a better understanding how to proceed or how to see the table. Okay, so okay, suppose this is a standard normal distribution. Okay, and this is the z value at z equal to 0 and plus minus. Now our aim is to minus 0.625. So suppose it comes out to be here minus 0.625, and the second one is 1.25. This is here suppose. So we need to calculate the area that encloses in this. Okay, so we have given the table, left side table are there. Okay, so how to calculate? First, we need to calculate the area of this Okay, from this particular point to this here, then from here to here, and then we minus those areas. So that means suppose I'm using the phi here. So phi 1.25 is defined as the area that lie one at before 1.25 and less than 1.25. Okay. The second one is minus phi of minus 0.625. That means the area that comes out to be like this. Okay. So this is the area, the second one, phi of minus 0.625. The area that this area comes out to be like our required area. So from the table, this comes out to be 89435 actually, minus this value. Let me show you again the value of this minus is there actually. So that can be seen with the help of the second table. Here the table is given for the minus. So minus is here 6 and 2. Since 2 is there, so minus 0.62 is this and 0.63 is this. So after rounding off, you will get 0.62. So 26763. Okay. So I think I've used 26736. Okay. So 0.26736 is there. Okay, 26763 is there. And after solving, we will get the probability as 0.26, sorry, 62672. It is an approximate value with the help of the normal table. So the probability that a randomly chosen person having height 170 to 185 is the probability of a person having the height 170 to 185 centimeter is around 62.67%. Okay, so this is how the question related to the normal distribution solved. Okay. If still any doubt related to the normally distributed random variables questions, then you can ask, or we can move to the different questions now. Okay, if you have different table, na, then in that case you need different approach how to see this. So that's why always draw this particular curve. Okay, this curve is more useful. Okay, how to find the required area. Okay, now the next question is a person plays a game where they have a chance of 30% of winning each round. Okay, the question is a person or player plays a game where they have a chance, he has a chance of 30% of winning each round independent of previous round. Okay, now he keeps playing until he wins. जब तक वो जीतता नहीं, like till then he will play. If he has already lost 4 rounds, the question is if he has already lost 4 rounds, 4 rounds, then what is the probability that he will win on the 7th round? Then what is the probability that he will win on the 7th round? So can anyone tell me which distribution, which like the problem related to which kind of distribution and how to proceed? Anyone?
Geometric distribution.
Geometric distribution. Okay. Yes, because he has already lost the 4 rounds and the probability, okay, let me write it. Okay. See, he keeps playing until he wins. Okay. The first win will terminate the experiment. Okay. So that means when we are dealing about the question in which the first success occurs, those can be solved with the help of geometric distribution. So it is a problem related to the geometric distribution only. Now, also how to proceed? There is one more question. Since it is given if he has already lost 4 rounds, then what is the probability that he will win on the 7th round? Okay, so if you can remember, I'm telling like I was telling the geometric distribution in case of discrete random variable and the exponential distribution in case of continuous random variables are having memoryless property. Okay, so this can be solved with the help of memoryless property even. And how to proceed? We need to find the probability that win on 7th round. The question is win on 7th round when the condition is lost 4 rounds. These are the question. He has already lost 4 rounds. Then what is the probability he wins on the 7th round? So that means there are 2 more loss and after that the success will be there. Okay. So we can also like write this x is greater than 7 given x is greater than 4. This is probability that x is greater than 4 plus 3 given x is greater than 4. And this is nothing but probability that x is greater than 3 using memoryless property. Is it clear? Or any doubt? You need to read the question and try to understand how to proceed this question. Okay. The first one is the random, which kind of random variable is this? Since it keeps playing until he wins, so it is nothing but the geometric distribution. And although also we are given some kind of conditions that he has already lost the 4 games, then what is the chances that he will win on the 7th round? So x greater than 7 given x is greater than 4. So using this property, the probability that x is greater than 3. And now the probability that x is greater than 3, that is 1 minus p to the power x minus 1 into p. This is the PDF for the geometric distribution. Here we are given p equal to 0.3 because the probability of success is 30%. Okay. And also x is greater than 3. Okay. So this implies 1 minus 0.3 to the power 3 minus 1 into 0. So 0.7 whole square into 0.3. And after solution, you will get the probability that x is greater than 7 given x is greater than 4 is nothing but 0.147. Okay, so I think it is clear how to solve the question related to the memoryless property or the geometric distribution even. Okay. Okay, let's discuss one more question related to the related to the memoryless property, but this time using exponential distribution. Now the question is, a machine has a lifespan that follows an exponential distribution. Just try to solve with yourself. I'm writing the question. A machine has a lifespan that follows an exponential distribution with mean lifetime of 5 years. This is the given question. If the machine has already been working for 3 years, then now the condition is there. If the machine has already been working for 3 years, then what is the probability that it will survive for at least another 5 years? Okay, then what is the probability that it will survive for another 5 years? Okay, now the question is, it has already completed 3 years. Okay, it has already completed 3 years and another 5 years, and the mean time is 5 years. These three are the information, and also it follows exponential distribution. So that means here x follows exponential distribution. Since exponential lambda, for example, we have assigned the value of lambda, then fx of x is lambda e to the power minus lambda x, with expectation of x is nothing but 1 by lambda. So we are given the mean time is 5. Okay, so the value of lambda is 1 by 5 actually. Okay, so we are given the random variable x, the lifespan of the machine follows exponential distribution with parameter 1 by 5. The given PDF is now 1 by 5 e to the power minus x by 5. Okay, this is greater than 0. Also, we are given the mean time is 5. These are already given. Now we need to find the probability that x will survive another 5 years. So that means 8 years, given x is greater than 3. It has uh, already working for 3 years. Okay, so this can also be written as like this: x is greater than 5 plus 3, given x is greater than 3, which is probability that x is greater than 5. Okay, so probability that x is greater than 5, this is again the reliability function, or if not, then we can write 1 minus probability that x is less than or equal to 5. And the CDF of this exponential distribution is 1 minus e to the power minus lambda x. So this comes out to be e to the power minus lambda x at lambda equal to 1 by 5, lambda equal to 1 by 5. So the probability that x is greater than 8 given x is greater than 3 is nothing but e to the power, okay, lambda equal to 5 and x is also equal to 5. Na? Lambda equal to 1 by 5 and x equal to 5 will give uh, minus 1 after solving. You can understand, na? X equal to 5 is there only. Okay, x equal to 5 is there only, lambda equal to 1 by 5. So after calculating, we found out e to the power minus 1, which is approximate value is 0.3679. Okay, so this is how we use the memoryless property to solve the questions. Any doubt up to this point? We have some more questions. Like this related to the binomial distribution. Okay, suppose x, let x be a random variable which follows, okay, now which follows binomial random variable. Actually, it is binomial distribution, binomial random variable with 6 trials, with 6 trials. Now this follows the following condition. Okay, this random variable follows the following condition. The condition is 9 times of probability that x equals 4 is equal to probability that x equals 2. Okay, then we need to find the probability of success. Can anyone tell me how to proceed? We are given x is a random variable which follows binomial distribution. Also, we are given 6 trials are there. That means the value of n is given actually. And instead of giving the probability of success, we are given a condition. 9 times of probability that x equal to 4 is equal to the probability that x equal to 2. We need to find the probability of success, that is a p. So can anyone like want to say anything or should I proceed? Look, 9 times the probability that x equal to 4 equal to probability that x equal to 2 is there. Okay. Also, if x follows binomial n and p, then in that case, the probability mass function is written as ncx p to the power x 1 minus 1 minus p to the power n minus x for x equal to 0, 1 up to n. Okay, so this is the PDF. Now we are given n equal to 6. So x equal to x is 6cx p. P is not there actually. P to the power x 1 minus p to the power 6 minus x equal to 0, 1 up to this point. Okay, now we need to calculate this. 9 times of probability that x equal to 4. So 6c4, x equal to 4, 6c4, p to the power 4, 1 minus p to the power 6 minus 4, that comes out to be 2, equal to probability that x equal to 2. So this implies n, not n, it's 6c2 p square 1 minus p power 6 minus 2, that comes out to be 4. Okay. Also, since we know NCR equal to NC n minus R. Anyone have doubt? This is the property of combination when we have read the permutation and combination. Okay, NCR equal to NC n minus R. Okay, so this implies these quantities cancel out each other. Also, p square is there. P here comes out to be 2. P4, P2, 2. So 9 times of p square equal to 1 times of 1 minus p square. So we can write 3p square equal to 1 minus p whole square. So this implies 3p equal to 1 minus p. Okay. So 4p equals 1. So p equals 1 by 4. Simple. Okay. So the probability of success for the given question is nothing but 25%. Okay. Is it clear now? Is there any doubt?
No, sir.
Okay. Okay, let's discuss one more question. Suppose in a book of 520 pages, in a book of 520 pages, 390 390 typographical errors are there. Okay. Errors occur. Now find the probability that a randomly chosen page has no error. Find the probability that the randomly chosen page has no error. Okay. How to, oh, sorry. How to solve this question? Anyone? Look, while discussing the Poisson distribution, I was telling na, कि when we are discussing about the kind of probability which has very less probability of success, or we are given a rate kind of nature, then we use Poisson distribution. Here it is given that in a book of 520 pages, 390 typographical errors occurs. Okay, so kind of rate is given here, but we need to calculate that rate first. Okay, since 520 pages contains 390 errors. So that means what? So one page contains 390 upon 520 error. Okay. So this is a rate. That means 390 upon 520, which also like simplifies as 3 by 4, I think. Yes. 3 by 4 or 75%. That means what? We are given that on every page, 75% of the chances that the error occurs. The typographical error are there on the page. Okay. Now we need to calculate, since this error follows Poisson distribution, then let's start. So our random variable X is what? Number of errors per page. Okay. And we are given the rate as well, lambda 0.75. Now we need to calculate what? We need to calculate the find the probability that the randomly chosen page has no error. That means there is no error. That means X should be equal to 0. So this implies e, e to the power minus lambda, lambda to the power x upon x factorial, putting the values. Now e to the power minus 0.75, 0.75 to the power 0, because x equal to 0, and 0 factorial. 0 factorial equals 1, and any number having exponent 0 also equals 1. So the probability that x equals 0 is nothing but e to the power minus 0.75. Okay, you may solve this for the numerical values, or you may leave here. Okay, so this is how when we are given rate, then we can solve the questions. Like in a telephone directory, every minute there are 2 calls are there. Then what is the probability that for the next 18 minutes, 17 calls are there? This kind of question can also be solved with the help of the Poisson distribution. Okay. Uh, Now one more question is there. The question is if X and Y are independent Poisson variable. If X and Y are independent Poisson variate. Okay, such that probability that X equals 1 equal to probability that X equals 2 and probability that Y equals 2 equal to probability that Y equals 3. This is the question. X and Y are independently distributed Poisson variant. Okay. Probability that X equal to 1 equal to probability that X equal to 2 and probability that Y equal to 2 equals probability that Y equal to 3. Calculate variance of X minus 2Y. Okay. We need to find the variance. See, we need to find the variance of X minus 2Y. That means we first calculate the variance of X of Y. That means we need to find the distribution of X and Y because we are not given the value of the parameter. We are only given it is India. These are independent Poisson variate only. So first, with the help of the given condition, we need to calculate the parameter value for the X and for the Y both. And then with the help of those estimated parameter value or calculated parameter value, we can calculate the variance of X minus 2Y. Is it clear now? Okay, let's solve this. Since we are given probability that X equal to 1 equal to probability that X equal to 2. Okay, and these are random variable. So for e to the power minus lambda X, not X, let me write it 1 actually for the X and Y 2 for a second. E to the power minus lambda 1 to the power X upon X factorial. Okay, at X equal to 1 and in a similar manner e to the power minus lambda 1 to the power X upon X factorial at X equal to 2. Okay, so here you see that e to the power minus lambda 1 actually cancelled out. This is cancelled out and because it is independent of X only. Now lambda 1 to the power x1 upon 1 factorial equal to lambda 1 to the power 2 upon 2 factorial. 2 factorial equal to 2. So after calculating, and here lambda square is there and lambda is there. So 1 lambda is also cancelled out. Okay. So after calculating, we found lambda 1 equal to 2. Simple. By transferring lambda 1 equal to 2, we get. Similar manner, we also probability y2, y3. Okay. Also given probability that y equal to 2 equal to probability that y equal to 3. This means e to the power minus lambda, I can write lambda 2, lambda power x or y factorial upon divided by y factorial equal to e to the power minus lambda 2 to the power 3 upon 3 factorial. Again, it got cancelled. Okay. Also lambda 2 and lambda 3 is also there actually. So this got cancelled. 1 is there. So this implies 3 factorial upon 2 factorial equal to lambda 2 and 3 factorial 6, 2 factorial 2 comes out to be lambda 2 equal to 3. So now we have the distribution X follows Poisson 2 and Y follows Poisson 3. Since X follows Poisson 2, this implies expectation of x equal to 2, which is lambda on itself, and variance of x equal to 2 as well, because for Poisson distribution, mean and variance are same, and expectation of y equal to 3 and variance of y also equals 3. Now we need to calculate variance of x minus 2y, which is variance of x because it is independent. So the correlation term is omitted or comes out to be 0. So variance of x minus maybe you remember variance of ax minus b is nothing but variance of a square variance of x and plus, let me write by p square variance of y if these are independent. Okay, if these are independent, then these are for independent case only. So variance of x minus 2y is variance of x plus 2 square variance of y. That means variance of x2 plus 2 square 4 into variance of y3, which comes out to be 2 plus 12. So variance of x minus 2y comes out to be 14. Is it clear? Look, I have completed lots of questions. Okay. There are many questions also there, like what is the normal property? Okay, normal distribution at same mean and median and mode. And there are lots of questions and lots of properties are there that I expect you people will learn. Okay. Any doubt, anything you want to ask, you want to discuss, you want to share, you can. Or if not, then we can like conclude our session from here only. Anyone? Okay, then if no question is there, then I think we should stop here. So thank you everyone for joining me. Let me stop the recording.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.